Okay, so here's a few things we have coming up. Homework 8 is actually due tonight by midnight, so we'll spend some time wrapping that up today. Homework 9 is due in 2 weeks, so you've got a lot of time for that. It's over chapter 8, chapter 14, 15, and 16. Now this seems like a lot of material, but we're not doing all of 8, all of 14, or 15 and 16. So we basically did the first 3 sections of chapter 8, and then today we're going to do the first 4 sections of chapter 14, which is simple harmonic motion. Okay, so remember after Thanksgiving we're not meeting in person anymore. So the lab that we were going to do in person this week, we're not meeting in person this week because Group B would have met after the break and we're not going to. So we're not meeting in person tomorrow if you're Group A. I do have this lab, simple harmonic motion, online. It's not there yet, it will be soon. I'll let you know when it is. Now that the report for that won't be due for several weeks, so it'll be there, and I'll give you more information about it towards the end of the week. Okay, and that is the final lab that we're going to do this semester. Okay, Monday, November 23rd, it's going to be an online lecture video. So, on Monday sometime I'll give that to you. And then we've got spring break. We've got Thanksgiving break, and then what's coming up in the future after the break, Monday the 30th is review for exam 3, and again that'll be a video. So soon I will make a practice test just like I have done, and then the review will be me going over the practice test and giving you some more hints. Now the actual test, the third test, is Wednesday, December 2nd. There should be a 2 there. And it's going to be an online test. And I'll give you some more information on this next week. The specifics of it. I'm still working out what I'm going to do. I want to make it as similar as possible. Probably it'll be through Brightspace. It'll be multiple choice, but there'll be a space to show some of your work. So I just have to work out the logistics of that. Okay, so more about that in the future. And then today we're going to cover parts of 14. So this is on simple harmonic motion. So we go from chapter 8 up to chapter 14. And we're focusing on section 14.1 through 14.4, mass oscillating on a spring. And the lab that we do, the simple harmonic motion lab, deals with the mass on a spring. Okay, so lots of information up here, but really with the break coming up, I just kind of wanted to outline the next several weeks so we have an idea where we're going. Okay, any questions about this? Okay, good. So this is the last time we're meeting in person this semester, actually. Okay, so oscillations, that's what this chapter is all about. So the goal is to understand systems that oscillate with something called simple harmonic motion. The reason we're doing this is if you could identify a system as representing simple harmonic motion, we'll have some equations that will make analyzing it a lot easier. So this is to make our lives a lot easier. So as the animal here goes across this log, they're swaying back and forth in a repetitive motion that might be able to be described as simple harmonic motion. So when the woman moves down, the springy ropes pull up, the restoring force produces an oscillation, one after the next. So this person would keep bouncing up and down, up and down. You'll see many examples of systems with restoring forces that lead to oscillating motion. So not only is there a restoring force, the bigger and bigger the disturbance is, the larger and larger the restoring force is. So more about that in just a minute. Okay, so if you notice, this is kind of an hourglass moving back and forth with a hole in it. So Stan records the motion. As this truck pulls this piece of paper away, sand is leaking out of here, and as this swings back and forth, we get this kind of a pattern. So it's a sinusoidal pattern, sine wave or cosine wave. Okay. So this is a pendulum. We're not really going to cover a pendulum. A pendulum is an example of simple harmonic motion. But you can kind of get an idea what, if you were to describe this motion, what it would look like. So this is a sine wave or a cosine wave, depending on where you start. So we'll see how that works out in this chapter as well. Here's a video from the author of the book. Let me make sure the volume's not too high. Maybe about there. Okay.
We're going to start a discussion.
Probably could use a little more volume.
Chapter 14, but looking back to chapter 8. Now I've got this cardboard that's hung from the spring. And right now there's an upward spring force and there's a downward weight force. And the net force is 0. But if I take this toy and I pull it down a little bit, so I stretch the spring. I'll ask you a question. At this instant, if I let go of the toy, right after I let go of it, what will be the direction of the net force on the toy? I'll give you some choices.
Good, so the direction of the net force. Weight is pulling it down, the force of gravity, but we know it's going to go shooting up, so the spring force is up, weight is down, the net force is going to be up. So there's a couple of forces, spring force and weight, but we know once he lets go of it, it's going to accelerate up, so the spring force is greater than the weight. Let's see.
Remember, back in chapter 8, when we talked about springs, we said if you stretch a spring, there's a restoring force. So I pulled the spring down, and so therefore there's an upward restoring force on the spring. So therefore, there's an upward force on the toy. And when it was here, the force of the spring was equal to the weight force. If I stretch the spring farther, now the spring force is bigger than the weight force. Spring force bigger than the weight force, there's a net force, and it's directed up. So if I let go, this toy will move up, but it doesn't stop there. This is going to keep on going, and it'll bounce for quite a long time. And this type of motion is called simple harmonic motion. And we get this kind of motion in systems where the restoring force is proportional to the distance from an equilibrium position. So the toy has a certain equilibrium position where it rests happily, and if I displace it from the equilibrium position, the farther I displace it, the bigger the restoring force is. I'm going to bring it down to some distance below its equilibrium point, and I'm going to let it go. And we're going to record the motion. And then we're going to analyze and describe the motion that we see. So let's take a look at this. Take a look at this motion. This is an example of simple harmonic motion. We're going to look at the position, the velocity, and the acceleration. And we're going to ask you some questions. Let's consider the motion of the toy as it bounces up and down. And we'll start right here, the high point of motion. At this point, the toy is motionless. It's at its highest point, and so the position is positive, the velocity is 0. But there's a net downward force, and so the acceleration is negative. And so the toy will begin to move downward. And right here, it passes through its equilibrium position. And right here, the velocity has reached its maximum value. It's accelerated until it gets to this point. So the position is 0, the magnitude of the velocity is maximum. But think about the force that's acting at this point. Given what you know about the net force on the toy at this point, what should the acceleration be? We'll give you some choices.
Good, so you can kind of see what the position versus time is doing. This is the velocity versus time. We want to know what the acceleration is doing at that point. And you can kind of just follow what it looks like here, the graph. It's going to turn out to be 0, which makes sense because there is no net force. No net force means there's no acceleration. Now, it doesn't mean it's going to stop. It doesn't mean the velocity is 0. It means that there's no net force on it. So the weight is down, spring force is up. No net force from Newton's second law, no acceleration. And again, you can kind of follow along with what this graph looks like. Okay, any questions about that? All right, good.
And at this point, there's no net force. And so the acceleration is 0. Since the acceleration is 0, the velocity does not go to 0. It continues, and so the toy continues moving downward. And then at some point, it ends up at its lowest point. Right here, it's at the lowest point of its motion. So the position is negative and it's at its maximum extent. What is the velocity at this point and the acceleration at this point? We'll give you some choices.
So same thing, it was, the toy was moving downward. It's at its lowest point, it's about to head back up. So for it to change directions like that, it must have stopped here for an instant. So the velocity is 0 at this point. And you can see too from the graph that it's going to follow back to 0. Now at this point also, the spring is stretched the most it's going to be. The spring force is the biggest it's going to be. We still have the weight down, but the net force is up. So net force being up means the acceleration is going to be at its biggest value. So the acceleration is also going to follow this path and be at its largest value. So displacement, smallest, acceleration, largest, those are actually 180 degrees out of phase. When one's a maximum, the other's a minimum. Okay? Oops.
Well, right at this point, the velocity is 0 because it's reached the lowest point of its motion. But as we saw at the start, there's a net upward force on the toy. Since there's a net upward force, there's a net positive acceleration. So the velocity won't stay 0. It'll become positive, and the toy will begin to move upward. It'll pass through its equilibrium position and keep moving upward, end up at its highest point again. Then the motion will continue cycle after cycle after cycle. Now look at the graphs of the position, the velocity, and the acceleration for this motion. They're all sinusoidal functions. And in the book, we have a table that explains the properties of these sinusoidal functions because we will see them again in future chapters. But this is a picture of simple harmonic motion. And any system that oscillates this way, any system that has a linear restoring force, will undergo motion that looks exactly like this. For instance, a pendulum.
Okay, so again, we're not going to cover a pendulum this semester, but it's good stuff. Let me back this up. I want to show you this table again.
All sinusoidal functions. And in the book, we have a table that explains. But this is a picture of simple harmonic.
So this slide is pretty good, actually. It doesn't have all of the information that we're going to need, but it has a whole bunch of it. Here's how you could describe position versus time. A is called the amplitude. We'll see that in just a minute. Cosine of 2 pi f times the amount of time. So the maximum displacement is something called the amplitude. This is the velocity versus time graph. Here's how you can describe velocity. The maximum velocity, 2 pi f times a. And the same kind of idea over here for the acceleration. Okay, all right. So that's a nice slide when you start to think about your formula sheet. Probably something like this should be on here. And then we'll add a little bit more as we go along. Okay. The right camera just doesn't want to work. There we go. Okay, so let's get back to the notes then. Any questions on that? Okay. So from the video you saw, there was that equilibrium position. That's where the forces are balanced. If you just let the thing hang at the equilibrium position, it would just stay there. You have to move it from equilibrium to get it to start going. So in this example, I believe this is just a marble that's free to roll. So if you have it here, it'll stay here. If you move it up here, there's going to be a force on it that pulls it back towards equilibrium. It doesn't just stop at equilibrium. If there's no friction, it would go this way, that way, keep oscillating. In real life, there's friction, so eventually this is going to stop. But the idea is there's a force that's always taking you back towards the equilibrium position. Just like in the spring example you saw, just like this marble rolling. So there's always going to be a force called the restoring force that's trying to take you back to equilibrium. Okay, so that's a hallmark of simple harmonic motion. So this kind of motion is called an oscillation. It keeps going back and forth, repeating itself. And you might have had an idea from the picture there, the video that we saw. whenever there's simple harmonic motion, you could describe position, velocity, and acceleration by sine and cosine waves. The same thing happens here. Okay, so there's a couple of terms that we're familiar with already called period and frequency. They have the same meaning here as well. So the period is the amount of time for one oscillation. We've seen that before. We first saw it with circular motion, the amount of time to go around once. Here it's the amount of time for one oscillation to happen, measured in seconds. We also have frequency, which is 1 over the period. How many oscillations per second or cycles per second, whatever it is. So this is 1 over seconds, which is a hertz. So again, we saw that in chapter 6. We really saw it in chapter 7 as well. Okay, so a little information we can fall back on from before. So if the period is 2 seconds, how much is the frequency? So remember, the frequency is 1 divided by the period. So 1 divided by 2 is going to give us a half. Okay, so we can do that one in our heads. So a mass oscillates on a spring with this period. What's the frequency? Well, the frequency is 1 over the period. So a half of a hertz. This one's a little more complicated. A mass oscillates on a horizontal spring with the period of 2 seconds. Okay, that means if you take it, you pull it over here, you let it go. So if I pulled it over here, this is the amplitude, you let it go. It's going to go here through equilibrium, this side, and back. That's what the 2 seconds takes to go from here. So I've stretched it over here, let it go, and come back over here. So the total time for one of these is 2 seconds. If the mass is pulled to the right and then released, how long does it take for the mass to reach the leftmost point of its motion? Okay, so if I left it here, if it went to the leftmost, that would be half of the cycle. So instead of 2 seconds, it would be 1 second. That's for it to go from the right to the left. And then to go from the left back to the right would be another second. That gives you a total of 2. But just to go from one side to the other is going to be 1 second. Okay, good. Here are some measurements for frequency that you might have seen before. 1 kilohertz, 1 megahertz, 1 gigahertz. So really high frequency, not so high. So if you tune in a radio, you have seen these measurements before up here. Now the period is 1 over the frequency, so you can calculate this as 1 millisecond, 1 times 10 to the minus third seconds. Be careful, this looks like meters per second, but it's not, it's milliseconds. 1 microsecond, micro is 1 times 10 to the minus sixth, or nanosecond, 1 to the minus ninth seconds. Okay, just so you have an idea what some of these, what typical numbers are. So an FM radio station broadcasts an oscillating radio wave at a frequency of 100 megahertz. So mega means times 10 to the sixth, 1 million hertz. What is the period of the oscillation? Okay, so if you have the frequency, you can calculate the period. The period is 1 over the frequency. So 100 megahertz, if you want to write it in scientific notation, is 1 times 10 to the 8th hertz. Okay, so 10 to the 8th, when you bring it up to the numerator, becomes 10 to the minus 8th. So this would be 1 times 10 to the minus 8th. If you want to write it in nanoseconds, if you want to write it in terms of times 10 to the minus 9th, if you make this part smaller, you got to make this part bigger. That's what happened here. That means 10 times 10 to the minus 9th seconds. Okay, very good. Okay, so the graph of an oscillator has the form of cosine function. So this is where you pull it off to the one side and let it go. So it's starting at its maximum displacement, then it goes through equilibrium, maximum negative displacement, equilibrium, etc. It repeats itself over and over again. Okay, very good. So it's called a sine function. Usually the position graph, we will have a cosine because we want to pull it out to its maximum amplitude and then let it go. Okay, so if the position is cosine, then the velocity we'll see is going to be minus the sign. Okay, so that's what's coming up. So SHM looks like shaking my head, but it's not. It's simple harmonic motion, right? So again, we'll be focusing on a mass on a spring, oscillating back and forth. So what would a real world example be? Sound waves entering the ear, so I'm looking over here, cause the oscillation of a membrane in the cochlea. The vibration can be modeled as a mass on a spring, it turns out. So when scientists are trying to figure out how to restore hearing, they've got to fall back on something. How are we going to address this problem? Well, it's something that vibrates back and forth. What's an example of that? Simple harmonic motion. So maybe we can apply the ideas of simple harmonic motion to the ear. And it turns out that's how they came up with this stuff. So the period of oscillation of a segment of the membrane depends on the mass and the stiffness, right? So that's just kind of like the mass on a spring. Depends on the mass and the spring constant. So the stiffness of the membrane, we could model it as sort of like a spring with the spring constant. Okay? So when you're hearing, you are worrying about picking up different frequencies. So that's where that comes into play. Okay, so we have, here's a mass on a spring. You're going to move it from equilibrium. So it was at equilibrium here in the top one. You pull it over to the right a little bit. From Hooke's law, so minus kx. K is the spring constant, measured in newtons per meter. X is how much you've moved it. The restoring force pulls us back towards equilibrium. So when you move the mass this way, the restoring force goes back to equilibrium. Now when the mass would move over to this side, the spring force is that way, pushing us back towards equilibrium. So the force is always taking us back to equilibrium. And the farther and farther we are from equilibrium, the bigger and bigger the force is. The more you stretch this, the bigger the force is. So this is definitely going to be simple harmonic motion. Okay, so that's a summary of what I've just said. Now if you were to plot this out, it would look something like this. Okay, so we're starting here. Maybe we start here at the amplitude. We go this direction. So you've stretched the spring out to a distance A, and you let it go. So in the beginning, the spring is really stretched, and then it becomes less and less stretched. So if you're wondering why these dots are closer together and farther apart, that's the reason why. Then we pass through equilibrium, and then we're going to start slowing down again. So really fast, going right through here, and then here we have to stop. So we were stopped here, and then we accelerate towards equilibrium. This is where we're going the fastest. And then as soon as we start compressing the spring, we start slowing down again, stop here, speed up towards equilibrium. That's where we're going the fastest, etc. Over and over again, assuming that there's no friction. Okay, so this is simple harmonic motion. And if you were to just plot out the position here, you'd get a graph that looks like that. So this is position here, and this is time here. So we're going to come back to this question. We need to get a little bit more information. So this looks a little bit more like the actual video from the author of the book. So we want to describe simple harmonic motion by going through this whole thing. So the author's video was pretty good. This just has a little bit more detail. So we're going to take the spring, the mass is on it, it's just hanging out there. You lift it up, that's what's happening in number 1 here, and you let it go. So the distance from equilibrium to the maximum position is called the amplitude. That's why it's A here. And then you let it go. So it starts from rest at position A, and the acceleration is the most negative it's going to be because it's pushing you down. The spring is compressed here. Now the author of the book actually stretched it and let it go up. We're compressing it and letting it go down. Okay? There's some key positions here. So as we head towards equilibrium, the speed is negative, and it gets gets more and more negative, I should say, until it passes through equilibrium. That's what's happening in number 3 here. We pass through equilibrium. So the position is 0. You know, that's where the spring would be at its relaxed length here. And that's where the acceleration is 0, because the spring is at its relaxed length, where the spring force and the weight were actually equal to each other. Okay? So the whole amount of time this takes is called the period. So to go a fourth of the way will be a fourth of the period. So it takes a quarter of the period to go to here, half the period to go to here, 3/4 of the period to go to here, all the way back to the period then. Okay, and it just keeps repeating itself over and over again. So here's where we start at A, then we're at minus A. So we started at the top, we're as low as we're going to be, and we're going to turn around and go the other way, so we have to stop for a minute. Okay, that's what we have here. And at that point, that's where the spring is stretched the most it's going to be, so the acceleration's its maximum. Okay, and then we head back up and we just do the opposite on the way back up. Whenever you pass through equilibrium, though, so on the way up, here's equilibrium, the velocity is going to be its maximum. The acceleration is actually 0. That's where the spring force and the weight are equal to each other. Okay, and then back to where we began. So most of what I said, these 1, 2, 3s, etc., correspond to the numbers that you see up there. Okay, etc., 4, 5, 6, 7, 8, 9, until we get back to where we started. Okay, good. So the position, again, we're going to take the spring and stretch it out and then let it go. So the position is described by a cosine function. So we have A is the amplitude, cosine 2 pi t divided by the period. Okay, so the period is whatever it is. This t here is whatever time you're measuring. So what part of the cycle are you at? So remember back to when we did chapter 7, 2 pi divided by the period, that's what omega is. So if you want to, you could write this as A cosine of omega times t, because 2 pi over the period is omega. So that's just another way of writing it. That's completely good, but just remember you can do that. Or if you want to write it in terms of the frequency. Okay, because 1 over the period is the frequency. Okay, so position is a function of time. So the velocity graph was a sine function, but it was really a minus the sine function because it was flipped upside down. So same thing, V max, sine of 2 pi t over the period. Same thing with the acceleration. Now the acceleration, there's a couple of ways of looking at it. This is what we did before with Newton's second law. So F is equal to ma. So A is F over m. So F over m. Now it's a spring, so the force is minus kx. That's the force divided by m. Also, the acceleration here is, this is from the new stuff that we've done today, looking at it as simple harmonic motion. It's got to be the maximum acceleration. It's really a minus cosine because it's the opposite of position. 2 pi t over the period. Same thing, 2 pi over the period is omega. You could write it like that if you want to. So if this is the acceleration and this is the acceleration, this is equal to this. And that's where we'll come up with a really useful formula. Okay? Good. And that'll be in just a minute. Okay, so this is a nice picture of what's going on in terms of position versus time. We'll focus on this one. It makes more sense to me. Pull the mass out to position A and then let it go. This one is like you pulled it out to A, let it go, but you didn't start timing it till it went through equilibrium. That's perfectly okay. This one just physically, to me, makes more sense. And then you can see where you're at different parts of the period. So we started at A, quarter way through, we're at 0, then we're at minus A, 3/4 of the way back to 0, and then back to A again at the very end. Okay, so we're always oscillating between A and negative A. So here's an example we can look at. An air-track glider oscillates horizontally on a spring at a frequency of 0.5 hertz. Okay, so you have to stop and think a minute. Okay, frequency 0.5. All right, so I already automatically know what the period is. I just have to do a little calculation. Suppose the glider is pulled to the right of its equilibrium position by 12 centimeters and then released. Okay, so that's what the amplitude is. The amplitude's 12 centimeters. Where will the glider be 1 second after it's released? And what is its velocity at that point? Okay, so if the frequency is 0.5 hertz, the period is 1 over 0.5 or 2. So it takes 2 seconds to complete the whole thing. If you start at 12 centimeters, go to negative 12 and back to 12, that takes 2 seconds. They want to know where we are at after 1 second. So that would be halfway through the cycle. So if you started at 12, after 1 second, you're going to be down here at negative 12. Okay, so we can just get that by knowing the period, and they're asking us, really, where are you at half of a period? And then what is the velocity at that point? So think back to the graph. When you get to the end points, you've got to stop for an instant to change directions and go back. So the velocity also has to be 0 there because you're changing directions. You were moving one way, now you're going to be moving the other way. If you've taken calculus, the velocity is the slope of the derivative at this point. So the slope of the derivative here is 0, right? Turning point. Okay, good. Actually, I think the next slide gives a summary of this. Good, so the period is 2 seconds. So really they're asking us what's going on after 1 second. That's why we know we're at negative 12, because it's half the period. And the velocity has to be 0 there because you're turning around and going the other direction. Okay, good. And then we're going to come back to this problem also when we have just a little bit more information. Now there is a connection to circular motion actually. You might have guessed that from the fact that we have period and frequency. But here's a turntable, and you have a ball on a turntable, and this is kind of the overhead view, and you shine a light on the turntable, and you can look at the shadow. So the shadow is going to move this way and back this way and back this way. It turns out that that kind of motion is the same thing as you'd get for a mass on a spring. The shadow would go this way, oscillate back and forth, just like the mass on the spring. Okay? So uniform circular motion projected in one dimension, like a shadow, is an example of simple harmonic motion. Okay, so we can look at some different pictures here. This is what's going on with the position. This one, we're looking at the velocity. So the velocity is actually tangent to the path. So this is the actual ball going in a circle. That's what you see here, the ball going in a circle. Okay, the simple harmonic motion part is the x part of it. So if this were the amplitude, that's really the radius of the circle here. This part is a cosine of phi, this part here. Okay? If this is the overall velocity, we want to know how much velocity is this way. So this is the overall velocity, which we know is 2 pi f times a, or omega times r, same thing we had before. That's where it comes from. But we want to know the part of it that's this way. And you can do that from this picture. So if this is v, this is v in the x direction. And the same thing with the acceleration. So when you look in the book, they just give you this. Where does it come from? Well, it's because v is omega times r. We've saw that before for circular motion. And if you're going in a circle at a constant speed, we know from chapter 6, the acceleration is towards the center. It's v squared over r. But we know that v, put everything together in this formula, you get this. 2 pi f, that whole thing squared, times a. That's towards the center. We want to know how much is this way because, again, we're saying that circular motion projected in the x direction is simple harmonic motion. So we want to figure out how much of the acceleration is actually this way. And we could use this nice picture here. Right? We're saying, if you know this, how much is this way? Okay, so we'll put all that together on the next slide. So just from the graph, the x part of the position was a cosine of theta, but theta is omega times t, right? Theta is omega times t. So this part, when it says a cosine of, I think I said theta, I meant phi. Cosine of phi, that's this, but phi is also omega times t, and omega is 2 pi f. So you actually get the same thing, right? This is the same thing we got for simple harmonic motion. That's the x part of the position. Okay, and then we can do the same thing for the velocity and the acceleration. So the velocity part from the picture, from this picture, if this is phi, this is the sine of phi, and we're actually moving this direction. That's where the negative sign comes from. So we get the same thing. Here's the maximum velocity then. Okay, good. And then finally the acceleration. Minus a cosine of phi. But the a part is 2 pi f. Remember we said this before. That's the magnitude of it. And then times a cosine of 2 pi ft. But from what we knew before, the acceleration is also minus kx over m. Those accelerations have to be equal to each other. Okay, so if you put those two accelerations equal to each other, this acceleration and this acceleration, you set those equal to each other, whatever comes in front of a has to be equal to whatever comes in front of a from the other one. This is what I'm trying to say here. Let me do it this way. So this acceleration and this acceleration has to be equal to each other. So the maximum amount occurs, what's the largest that the cosine function could be? Well, the largest that could be is 1. So when that is 1, that's where the acceleration is a maximum. So when is this a maximum? When x is actually equal to a. So let me rewrite this minus k x, oops, didn't mean to do that. Did it again. Minus k a over m. This is the maximum acceleration. Just from using Newton's second law, this is the maximum acceleration from what we've done now. So whatever comes in front of the a from each of those has to be equal. So 2 pi f, that whole thing squared, has got to be equal to whatever comes in front of this a, so k over m. So 2 pi f, that whole thing squared, has to be equal to k over m. So let me write that on another piece of paper real quick. So this is the big payoff from this whole stuff that we've just done. So 2 pi f, that's from simple harmonic motion. That's what comes in front of a. That has to be equal to k over m. So this whole thing is omega squared. So 2 pi f is omega. Omega squared is equal to k over m. We could write this a lot of different ways as well. Let me write it in several different ways. This would give you 4 pi squared f squared is equal to k over m. Or I could write this in terms of the period like this. So 4 pi squared over the period squared is equal to k over m. So the payoff here is the frequency is going to be 1 over 2 pi square root of k over m. The period is going to be 2 pi square root of m over k. So these two equations right here, this is why we've gone through all these different slides. If you identify a mass on a spring, you can immediately calculate the period. It's 2 pi square root of m over k. So just knowing the mass and knowing the spring constant allows you to calculate the period. Mass, spring constant, you can calculate the period. Same thing if you wanted to do the frequency. Okay, now if you notice, the amplitude is not in this formula. You would think if you stretch the spring out more that it would, the period would have to get larger, right? Because there's a bigger distance to travel. But the thing is, there is a larger distance to travel, but it's also moving faster. Those effects go away. The amplitude doesn't matter. So you could take the mass on a hanging spring, move it down a little bit, let it go. It's going to have a certain period. You could take the mass on a spring, same mass, stretch it down farther and let it go. It's going to have the exact same period. The amplitude does not matter. It seems like if you stretch it more, the period would have to be greater, but the fact that it's moving faster cancels out. So when you do the next lab, that's actually part of it. And you'll see that that's true. Okay? Very good. So that's the big payoff from going through all this. You can get the period right away if you know the mass and the spring constant. Okay, so let's maybe use some of this newly found information. A 500-gram block is attached to a spring on a massless horizontal surface. Okay, we got a mass on a spring. The block is pulled to stretch the spring by 10 centimeters. Okay, so this is the amplitude, right? The 10 centimeters is the amplitude. Then gently released. A short time later, as the block passes through the equilibrium position, its speed is 1 meter per second. The spring constant is 10. What is the block's period of oscillation? And then the second part here I have written, save this part for the next section. This part's easier to do in the next section. Okay, so we know the mass. We know the spring constant. It's pretty complicated, the motion. As you saw, you stretch it out, it starts going towards equilibrium. It's going the fastest in the center, and then it goes to the other side, it stops. The acceleration keeps changing. It's not constant acceleration. We can't use kinematics because the acceleration is not constant. It's very complicated, but we can get the period because it's simple harmonic motion. And then it's not too bad at all. It goes back to the period is 2 pi square root of m over k. So 2 pi square root of m, so the m is 0.5 kilograms, and then the k, that's the k, the spring constant. And then it's not too bad to calculate. So just by knowing it's simple harmonic motion, your life is a lot easier. So period would be 2 pi 0.5 divided by 10. Okay, and it's measured in seconds. All right, excellent. So we will do part B once we talk about the energy in the system. Any questions on this one? So there was a lot of work to get to the point of this, but it's well worth it because it'll make your life a lot easier. Okay, and then I have a note here to do 14.6 from homework 9. So let's take a look at that. Okay, an air track glider attached to a spring oscillates between the 13 centimeter mark and the 55 centimeter mark. And you might have different numbers on there. So if you're watching the video, it might be kind of hard to see this because it's not zoomed in. But on the homework, this is the sixth problem. And it's from chapter 14, so 14.6. Air track glider attached to a spring oscillates between 13 centimeters and 55 centimeters. So those are the endpoints. The glider completes 11 oscillations in 33 seconds. What is the period? So that's the amount of time for one oscillation. So if we've got 33 of these, sorry, we've got 11 of them in 33 seconds, how much time does it take for one of those? So 33 divided by 11, it would be 3 seconds. That's the amount of time for one of those. So the period here is just 3. Let's see what the other parts are. What is the frequency? Okay. Well, if you know the period, the frequency is 1 over the period. If you want to go back to the given information here, we want to know how long it takes for one oscillation. So this would be, or I should say, scratch that. We want to know how many oscillations per second we have. That's what the frequency is. So 11 divided by 33. So 0.33 oscillations per second. Ah, good, and it's in hertz. 1 over seconds is a hertz, so that should be 0.33. You can check it out, just do 1 over the answer you got from part A, and you should have the same thing. What is the amplitude? Okay, so maybe we have to do a little bit of a picture. And then finally, what is the maximum speed of the glider? Okay, so think back of what we've gone through before for maximum speed. If you have the frequency and the amplitude, you can get the maximum speed. Okay, so first we have to get the amplitude. Be careful, they want it in centimeters. And then we want to get the speed, the maximum speed, I should say. And that's in centimeters per second. Okay, so we're good working with centimeters here. All right, so let me draw this out, and maybe we can come up with the amplitude from this. Okay, so we're going between 13 centimeters and 55 centimeters. Okay, so the equilibrium position is somewhere here, right in the middle. Okay, so it's not 13, it's not 55, it's between those. And then the amplitude would be, you oscillate this way from equilibrium, that way from equilibrium. Okay, so if we just add those together, divide by 2, I think that should give us the amplitude. So 55, or subtract those, I should say. We want the distance between them, and then divide that by 2. Okay, so 42, that's the distance between them, and then take that and divide it by 2, that will give us 21. So this would have to be 21, this would give us 21. Okay, and then 13, let's just make sure, 13 plus 42 is 55. Okay, and this is all measured in centimeters. So the amplitude in this problem is 21 centimeters. Okay? So that's this is part C. And then you saw this formula. The maximum speed, it's 2 pi f times the amplitude. So the frequency you got in one of the parts, the amplitude we just got, so then you can get the maximum speed. Okay, very good. All right, any questions on this one? All right, excellent. So this table puts it kind of all together for us. You have an idea what the picture looks like. The author of the book, you saw this. Here's the maximum position, maximum velocity. We just used this. Maximum acceleration. The only thing I would add to this at this time is the formula for the period. So we just did that too. The period, 2 pi square root of m over k, the frequency being 1 over that. So that's the only thing I think I would add to this picture. So mass oscillating on a spring, you have this whole nice set of tools you can use to solve those problems. Okay. Excellent. So this problem is similar to one of the homework problems. So we'll do this one instead. The John Hancock Center in Chicago is 100 stories high. Strong winds can cause the building to sway, as is the case with all buildings. On particularly windy days, the top of the building oscillates with an amplitude of 16 inches. Seems like kind of a lot, but it's 100 stories up, so maybe it's not too bad. in a period of 7.7 seconds. Okay, so it takes, from equilibrium, the top of the building will go 16 centimeters this way and 16 centimeters that way. And to go from one side to the other and back is 7.7 seconds. What are the maximum speed and acceleration of the top of the building? Okay. So without saying too much, we just looked at the formula for maximum speed, 2 pi f times the amplitude. Or if you want to, you can write it as 2 pi divided by the period times the amplitude. Let me try to write it on the screen here. So maximum speed. Sorry, I don't have a touch screen today. We saw it was 2 pi frequency times the amplitude. If you want, 2 pi over the period times the amplitude will work as well, because the frequency is 1 over the period. This is supposed to be a 2. Okay, hopefully that looks okay. So the maximum speed is 2 pi amplitude divided by the period. And you can see the units work out too. This would be meters per second. Okay, now on the previous slide, we had the formula for the maximum acceleration here. Don't forget to square it, but you could write it as 2 pi over the period, that whole thing squared, times the amplitude to get the maximum acceleration. Okay? So without putting the numbers in, that's the way that you can do this problem. And again, it's similar to 1415 on the homework. Oh, actually, it's solved here. So there's the frequency. If you want to do it in terms of the frequency, you can do that. And then you can get the maximum speed that way. Okay, you don't have to do it with the frequency. You could just use the amplitude. Anyway, 0.33 meters per second. So not really super fast, but you're in a building, I would prefer it to be 0, but it's in the wind, so it's not too great. And then the acceleration is not very big either, 0.27 meters per second squared. So it's a fraction of the free fall acceleration. But it's not 0. That's the thing that you can feel, right? There's a net force that the building has, although very small. So quite small, as you would expect. If it were a large building, occupants would certainly complain. Even if they don't notice the motion directly, office workers on high floors may experience a bit of nausea when the oscillations are large. A former student of mine's mother worked, I believe it was in this building actually, towards the top, and they could tell it was moving in the wind. Okay. I don't know if you ever get used to it. Maybe you do, maybe you don't, I don't know. It will affect your inner ear, though. That's where the nausea comes from. Okay. Any questions on this one? All right, so pretty cool. Now the last thing we can look at is the energy that's associated with simple harmonic motion. So maybe this part I will do on a piece of paper, actually. So the energy is just one more part we can use to try to solve some problems. So for mass on a spring, here's a spring, here's a mass. It's just at rest here. I'm going to pull it off to the side and let it go. So again, this is called the amplitude. So it started here. I pulled it off to the side. Now I'm going to let it go. And it's going to oscillate back and forth. So this is where it's at like half the period, so minus A. So when we're at these endpoints, when we're over here, it's not moving. Remember, the velocity is 0 here. So all of the energy is spring potential energy. So think back to what we did in chapter 10. So the formula for spring potential energy is 1/2 kx squared. But this is a special kind of x here. This is A. So all the energy here is 1/2 ka squared. The kinetic energy here is 0. The same thing happens over here. All of the energy is spring potential. The speed is 0. And the kinetic energy is 0. Now right here at the equilibrium point, this is where x is 0, there is no spring potential energy because it's not stretched or compressed, right? That's where that was its relaxed length. This is where the speed is the greatest, so that's where we have V max. Okay? And this is where the kinetic energy is a maximum. So this would be 1/2 mv max squared. So here all the energy is spring potential energy. At equilibrium it's all kinetic. And then here, then it becomes all spring potential again. So those are some interesting points over here at the end point, equilibrium, back to the end point here. So in between, when you're here, you're moving, but the spring isn't stretched or compressed as much as it could be. This is just kind of a general. The mechanical energy you have there is made up of 1/2 mv squared plus 1/2 kx squared. So you've got both kinds here. You start off with all spring potential. Okay, you get less and less spring potential, more and more kinetic. Here it's all kinetic, and then when you move away again, now you're getting less kinetic, more and more spring potential. So you get to the end, then it's all spring potential, and then it goes back and forth. So the total mechanical energy you have, I could write it like this. Well, it's going to be 1/2 Ka squared. That's when it's all spring potential energy. Here's where it's all kinetic. That's through the equilibrium point. Or it could just be in general 1/2 Kx squared plus 1/2 just a general mv squared. Whoops. Okay, hopefully you can see that okay. So in terms of energy, this is really everything to do about energy. So maybe in addition to the one slide you saw before, if you want to look at the energy considerations with a spring and a mass system, this would be it. Okay, so that could just help you solve some different problems. Okay, it's kind of similar to what we did before when we had, I think it was a skater actually. Yeah, it was the lab that you did where the skater went up and down. Kinetic energy was turned into gravitational potential energy. You came back down. It was all kinetic, all gravitational. It's a similar idea. It's just we don't have gravitational potential. We have spring potential here. Okay, so same kind of idea. So this is what the picture actually of this would look like from the book. Good, so the total mechanical energy is made up of kinetic and spring potential. Here's the turning points. So we've got kinetic, gravitation, or sorry, spring potential energy. So this looks just like the graphs that we've seen before. Okay? So the potential energy is in the blue, the kinetic is in the green. So when it's all potential, this is at the turning points, there is no kinetic. And then when you start going back the other direction, all right, you lose potential energy, but you're gaining kinetic energy. The total energy stays the same though. It's made up of both types. Okay, so this is kind of this picture is good. It's the same kind of thing I did before. I just wrote on how much energy was at these different spots. That's what the graph would look like though. Okay. This is again a synopsis of what I've said. Same thing here. And then those are the special points, the turning points, it's all spring potential. And the second bullet point there, that's where it's all kinetic. Okay, in between it's made up of both types. Okay, and then we saw this earlier. I already came up with this for you. So pretty much you have everything to do with simple harmonic motion now. You have all the simple harmonic motion tools for a mass on a spring. And then let's look at one more problem today, and then if you have any questions on homework 8, we can finish that up. So 14.26.